Hello everyone, I'm Burusai. During my embedded internship at Emertxe, I worked on the project called Real-Time Electric Vehicle Dashboard and Advanced Driver Assistance System, Warning System. This project developed using a STM32 F103 C8T6 Blue Pill microcontroller, PICSimLab Simulator, we are using PICSimLab Simulator and a Python dashboard. The aim is to monitor EV parameters in the real time and provide a driver safety warnings. Okay, I'm from Department of Electronics and Communication Engineering from Sri Venkateshwara Engineering College, Tirupati. Let's discuss what is ADAS. ADAS stands for Advanced Driver Assistance System. It improves vehicle safety by continuously monitoring the surroundings, using the sensors and warning the driver whenever there is a potential danger. Okay, let's see some few features about ADAS. FCW, it is a forward collision warning. Whenever there is an accident or any collision from the front side, it will be a forward collision warning. Okay, it will notify the driver that there may be a accident alert. Okay, and the blind spot detection. This blind spot detection will be takes place at left and right side of the vehicle, and time taken for collision. It will be calculated in our code that how much time is expected that there may be a collision. Okay, and parking assistance and overspeed advisory. If we are using if our vehicle is in overspeed, it will give you an alarm that we are moving it overspeed. Okay, and automatic emergency braking also. Okay, and here are the few things that why we need a smart dashboard. Okay, the motivation behind this project is that modern electric vehicles generate a huge amount of real-time data such as speed, battery, SOC, motor temperature, and ADAS sensor informations. Okay, without a centralized dashboard, monitoring all these parameters will become so difficult. To avoid that, we are building a smart dashboard. Our solution is a real-time dashboard that will display EV parameters. Okay, EV parameters, ADAS warnings, and motor temperature, fault alerts, and all the information. This will be available at one place. It is a driver mode information. Okay, let's go with the system architecture. This is the overall architecture of our project. Okay, first of all, we are calculating the inputs from the sensors. We are dealing with software tools, so we are considering the potentiometers as inputs. Okay, we are taking 4 potentiometers. One is acceleration pedal, another is for brake pedal, one is for motor temperature, another one is for SOC. It is a status of charge for battery. Another in the second stage, in the second thing, it is a STM32 Blue Pill. It is a board. Okay, it is a ADAS engine fault handler. Okay, it will handle the EV control. Okay. Third thing is it is a UART. UART is a protocol which will use it for communication. We are using the communication 115200 bits per second. Okay, and finally we are integrating all these things. Okay, all these our parameters and all these and we are receiving it in the Python dashboard. Okay, now let's discuss about EV and conventional vehicle. This slide compares conventional vehicles with electric vehicles. Initially, if we need any power source, okay, in conventional vehicles we need petrol or diesel for working in the to movement in the cars. Okay, in the electric vehicles, if your vehicle is an electric, we need a battery. Battery is an okay, and it will get charged and discharged. Okay, it will emit in the conventional vehicle. It will emit a few things pollutants like CO2, which will harm to the environment. Here there is no emissions. It will be zero tailpipe emissions. Here in the conventional vehicle, it will use 30% of the thermal energy. In the electric vehicle, it will use 90% of the electrical energy. Okay, if fuel is totally consumed, we need a petrol station to refill it. Here we need AC and DC charging stations. In the conventional vehicle, we need to change some few things regularly, like for the maintenance purpose, oil filters and exhaust. And in the electric vehicle, we need a few moving parts like tires and etc. And in the conventional vehicle, torque will be generated, based on the RPM. But in the electric vehicle, instant full torque will be generated. Okay, and a few more modules. ADAS will be ready add-on modules. We need to add on it in the conventional vehicle. Well, in the electric vehicles, it is integrated by the design itself. Okay. And let's discuss a few things which is compared with the real industry and based on our project. Okay, in the real industry we are dealing with the real-time sensors, proximity sensors, wheel sensor, and real pressure sensors. But in our project we are using simulation tools, right? So that we are using potentiometers. Okay, and for execution purpose we are using PICSimLab Simulation tool. And this is ECU, right? It is an electric control unit and or vehicle control unit VCU. In the place of that we are using STM32 Blue Pill. Okay, for writing the code and execution. So, and in the real time, they are using that CAN protocol. This is also same for communication, but here we are using UART protocol, okay, at 115200 bits per second. In the real time industry, they are using HDMI display, okay, industrial cluster to display the things, Python things. They are using HMI display, okay. In our project, we are using Python dashboard, okay, and few more things. They are using multi-tone buzzer alarm system, and here we are using some alarms as a non-advertising and warnings and critical, okay. And let's go with the ARM, okay. What is ARM? ARM stands for Advanced Discrimination. It is a low power and high performance microprocessor. High processor. Sorry, let's continue with this. High performance processor architecture, widely used in the embedded systems. These are widely used in the embedded systems and some mobile devices and IoT. This is common thing which is used, and these are the few companies that will manufacture these ARM chips. Okay, AST and NXP and TI Texas Instruments and microchips. Let's go with some ARM processor profiles. Here they have three things: Cortex-A, Cortex-R, Cortex-M. And A is for application purpose, R is for real time, and M is for microcontroller. In the A, it has a specifications that high performance systems, and we can run Linux, Android, and iOS. In the real time, it has a real time and a safety critical deterministic response. In Cortex-M, it is for microcontrollers and low power and low cost. Okay, when we have the purpose where we are using this Cortex-A in smartphones, tabs, and Raspberry Pi based projects. In the real time, we are using it automotive execution control, electrical control units, and industrial automations and medical devices. Okay, microcontrollers, it is a Cortex-M is used at IoT devices, sensors, and embedded controls. Okay, let's go with these are the some series in the Cortex-M. Okay, this Cortex-M7 is the high performance thing. Okay, in Cortex-M0 it is the small and most energy efficiency one. This is the general purpose M3, and this is the DSP plus optional FPU signal processor. And let's discuss ADC. Okay, ADC is a analog to digital converter. User will understand only analog values. He cannot understand digital values because it is too complex the coding. Okay, so we are writing here we are dealing with analog value that will be converted into digital. So we need a analog to digital converter. It is a analog to digital converter. Whatever the values we need to convert. Okay, we need some few analog values which we are using some potentiometers, right? It will be accelerator, brake, and SOC status of charge and motor temperature. Okay, here we are using 12-bit resolution. Okay, 1 bit. Here we are using 12-bit resolution for ADC. And here overview of the ADC architecture. We are going to learn architecture of ADC and 12-bit mapping, which it is from 0 to 4095, and some physics formulas. Okay, and how it is going to convert analog to digital values. And we are using STM32 cube XIDE for configurations of which pin need to be selected for analog to digital. Okay, that pins will be selected here, and we are going to read for values from the 4 sensors, and it will be in the PICSimLab. We are giving the inputs in the PICSimLab paper window, and we are going to view the outputs at virtual window. Okay, in the PICSimLab. Here UART is for communication protocol. This will displays at 115200 bits per second. Okay, now let's see what is an ADC. Okay, it will take voltage, temperature, pressure, and continuous values. Whatever the continuous values, it will take and convert into a binary. Okay, here CPU will understand only zeros and ones. Okay, so here ADC samples, now it will samples the analog signal at regular intervals. It will convert the analog values into regular intervals, which it will convert to discrete binary. Continuous here continuous analog signals will be converted into discrete binary numbers. Okay, it is from 0 to 4095. For it is a 12-bit. We are using a 12-bit resolution. We are reading the real data, which is analog data, and we are sampling and holding this, and we are using the ADC core for and we are storing it in the 12-bit register. Based on this, CPU will be accessed. We are using a V reference from 0 to 3.3 volts. Okay, this register can access through this V reference voltage. Here we are using 12-bit resolution. Okay, well, let's going to see the 9 phases of our project. Okay, let's see, our project was developed in the 9 phases. Okay, we started with environment phase. Okay, this is environment phase, and then we configured GPIO pins and peripherals. Next, we have implemented ADAS sensor inputs. and then we have developed EV dynamic models, and then we have developed ultrasonic based ADAS, and then we have added fault and alarm detections, and then implemented UART communication, and then developed a UART shell, and finally we built the Python dashboard in the 9th phase. Okay, this is the explanation diagram. These are the 4 potentiometers. So first one is the acceleration pedal, and second one is the brake pedal, third one is the status of charge, it is for battery, third one is, fourth one is motor temperature. These all 4 analog values will be converted into digital by this analog to digital converter. This is a board which we are using, blue pill board. It is a STM32 F103 C8T6. Okay, these 3 are the ultrasonic sensors. One is at the front side, and the one is at left, and one is at right side of the vehicle, okay, to detect the distance between the vehicle and the object. Okay, now here we are connecting with EV control code, and we are writing some EV control code and ADAS control codes. In the EV control code, it will calculate, and it will calculate speed, okay, and distance and everything, like etc. something in the EV control code. And in the ADAS control code, it will calculate FCW, it is a forward collision, okay, warnings, and BSW, blind spot detections at the left and right side of the vehicles, okay, and TTC, time taken for collision. All these things will be calculated at ADAS control code, and these 2 things will be connected. Okay, we are using the PICSimLab for execution purpose, and this will be connected to the port. Okay, we are transmitting some information, and we need to connect to the Python dashboard. So we are using a UART protocol. Okay, this is a UART protocol. This is used for communication purpose. UART stands for Universal Asynchronous Receiver and Transmitter. Okay, and next we are going to, this is the project workflow. Okay, how this will be is, at first ADC values will be read, and then vehicle parameters are updated, and ultrasonic sensors measured abstract distances, and then it will calculate the time taken for collision, and then priority alarm is get decided, and finally all the information is transmitted over UART. Okay, and all the information is going to transfer to the UART, and then it will be displayed on the Python dashboard. Okay, in this slide we are going to check whatever the values is met with our expected things. Okay, let's see here, real-time speed and SOC are displayed, and ADAS detect nearby obstacles, and blind spot detection works correctly, and the motor temperature and faults are generated, and Python dashboard displays all the parameters in the real time. Okay, and finally our project successfully achieved all the expected results. Okay, now we are going to implement our real-time electric vehicle dashboard and advanced driver assistance system. Okay, warning system implementation. What are the requirements we need is STM32 for writing a code, and we need to execute that code. So we need a simulator called PICSimLab, and we need to select a board as blue pill and microcontroller, and this microcontroller we are using for execution purpose. It is STM32 F103 8T6. Here we can see that application requirements. This is the STM32 It is the integrated development code which we are writing the code, which we are using a version 1.19.0 version. It is IDE. Okay, and execution purpose we are using PICSimLab. Okay, this is for execution purpose, and we are using a tool called VSPE. This is a port changer. Like we need to select in a transmitter and receiving port, right, for UART. So you can, by default laptop has few other ports, so you can change the port numbers. So to change that port numbers, we need this VSPE. Okay, and here we have some peripherals are required for this project. One is a microcontroller, and this is STM32 F103 C8T6, and potentiometers for acceleration, brake, SOC, and motor temperature. And we need analog to digital converter, ultrasonic sensor as HCSR04 for left, right, and front. Okay, and general purpose input output, and timers, and UART, and ADAS, EV control module, fault management system, alarm management system, Python dashboard, and PICSimLab Simulator, STM32 HAL Library, STM32 QByD. Okay, these are the peripherals that are required for our project. Okay, let's go with the project implementation right here. Let's see this. This is STM32 QByD that I have written all my code in this. We are using this for writing the code. These are the files we have written, and see. Let's see. We will build our project to generate a .bin file or executable file. Okay, so let's see, is there any errors and warnings? Yeah, I do not get any errors. It is 0 errors and 0 warnings. Okay, now let's open PICSimLab. Okay, this is PICSimLab. I need to select 31.25, and I need to load the file, right, a binary file which is created by the STM32 QByD. It is a .bin file. Now I will load this. How it will be? This will be EV dashboard is our folder. Right, opening this, we can find some few folders. In that, just go to debug, and we can see that bin file. Okay, just click on this and open. Okay, this will open it again. Here you can see that I need to select a blue pill board. Okay, blue pill board, and I need to select a microcontroller as STM32 STM32 F103 C8T6. Okay, and okay, now I need to load my file, right? I have loaded. Now okay, this is not required. Okay. Now I will, this is, just see this, this is the microcontroller which we are using. Okay, this is the reset button and few other parts. Okay, this is the blue pill board. Now let's go to the module and spare parts. Okay, in that you can see this is the spare parts. Okay, I'm taking these are the potentiometers. Okay, these are the 4 potentiometers to read the values from the user. This is the acceleration. Okay, this is the acceleration pedal, this is brake pedal, and this is a SOC, okay, status of charge, to read the battery percentage. Okay, this is a motor temperature, and this is the ultrasonic sensor. These 3 are the ultrasonic sensors. This is the virtual terminal which will connect our inputs. Okay, it will take inputs from the user and it will convert, and it will process the information. It will give some displaying output, right? For that we are using virtual V term for displaying the output. Okay, see this here, it will display the output. Okay, like this. Yes. Okay, now I am checking this. These are the potentiometers. This is a LED. Okay, now I am increasing my speed. Okay, now I am increasing my speed. Now I will get reset. Okay, it is displaying some previous data, so we will reset this. Here our it will get start resetted. Now you can see that battery is medium and the motor temperature is medium. I am using acceleration. Here you can see this is the front distance. Okay, which is the front distance is calculated, and it is the left distance. This is right, and this is time taken for collision. Okay, this is a blind spot detection. This is collision. Is there any collision happen or not? And this is alarm. Okay, here it is showing 1 because we have more speed, right? It is over speed, so that it is showing 1. Now we can see that speed. Okay, how much speed it is going? It is getting calculated. It is increasing. Okay, and SOC will start training. You can see this. Why? Because a vehicle is in movement, and torque, it is positive torque, and motor temperature is common. Okay, if motor and range, and this is the range we are moving. Okay, how much distance we are moving, and it will calculate how much distance we can move with our electrical charge. Okay, and here it is acceleration, and this is a brake. What if I reduce my acceleration? It will directly implement at here. Okay, you can see directly at here acceleration will get reduced. What if I increase my brake? Okay, you can see 2 things. One is brake is increased, and you can see that SOC is draining, right? It will get start charger. This is regenerative mechanism. Okay, now I will reduce this. Okay, if I increase my motor temperature, it will show me that fault. Okay, it will show that fault as 1. Okay, and it will display the 4th LED as B. This is a PB11. Okay, this is fault 1, and if I do not have any charge in my battery. Okay, so once I will reset it, so see this, if I do not have any charge, it will display fault as 2. Okay, say this is the fault LED which is yellow. Okay, so it will display fault as 2. Again I need to reset it. Okay, it will start reading. Here we are using the communication for 115200. Okay, and here you can see it is okay, it is okay. Now let's discuss the fault 4. Okay, this, if I reduce it, okay, this is my thing. Okay, this is my front ultrasonic sensor. If there is a less distance between the obstacle and our vehicle, it will show 2 things. One is a fault 4, and it is a critical, and there may be a collision. There may be a chance for collision, so it is a collision purpose. Okay, it will start. It will be disappear. Okay, this is the left ultrasonic sensor which will find object from the left side. Okay, if it is a less than 20, it will display blue LED. Okay, it may be like it is a it is like blind spot detection. It will display blind spot. Okay, which will show the blind spot area on the left side. 10 means it is from the left side. It will get disappeared. Now let's see for right side. Here we are using green LED for the right side. It will show as a blind spot detection as 01. Okay, this is blind spot detection at right side. Okay, these are the things. Now let's implement. This is the execution in the PICSimLab. Okay, let's go with Python dashboard. Okay, CMD, just open CMD, and as run as administrator, just click on S. It will be that CD, and next it will go this, and just copy few commands. This is my location where my Python code. Okay, I will enter this. I will check is there any folders. There are files. Yeah, I have some file read. This is my file, so I will run this file. How I can run this file means I will type a command for I will type command as a Python, and I will write my file as python4.0. Okay, I will copy this file name, and I will use the port communication 1. Okay, for communication I am using port 1. Okay, now within few seconds I will get my Python dashboard. Okay, see this. This is our EV vehicle. You can see. Right. Here you can see this is our speed. It is showing in the speed history, and this is the battery percentage. Okay, see, okay, I am increasing my speed, so it will reflect on the Python dashboard. You can see speed will get starts increasing. Okay, it is incrementing. Now here it is acceleration has increased, so it is getting increased. So you can see that battery percentage is 98.9, and it is now 98. Now I will decrease my speed, acceleration. Now I will increase my brake pedal. So it will start reducing speed. Okay, if it is over speed, it will get displayed. Okay, here you can see that it will get recharged. Okay, this is regenerative braking. Okay, here speed is continuously reducing, and you can see that brake is 85. Okay, and it will give negative torque. Okay, now let's discuss about fault alarms. Let's see this. I am increasing my motor temperature. It will be reflected here at here. Okay, in the dashboard. You can see this. Here it will show fault as 01. The hex is 1 because my motor temperature is too high. Okay. Yes, okay. If there is no charge, okay. If there is no charge, I will reset this. Okay. It will show as fault as 02 as advertiser alarm. It is advertiser. You just say this as fault as 02 because there is no charge. So it is showing that fault as 02. I will reset it again with battery. Okay. Now say this. My speed is 150, right? So it is showing an advertiser alarm. Okay. So it is an advertiser because it is an alarm as 1, right? So it is an advertiser. My speed is getting reduced. Why? Because I have given 0 acceleration initially, and brake is more, right? So it needs to get reduced. Okay. And I am reducing front distance here, front ultrasonic sensor, and we can see that there may be a collision. So my alarm will get critical. Okay. It is showing that critical, and time taken for collision is very less. It is 0 seconds. It is predicting. Okay, so increase this. Still, yeah. Okay, now it will display. Yeah, you can see that object distances from the left and right also. Okay, it is giving the time taken collision values. See, this is 100%, and I will reduce the insulation pedal. What if my left blind spot is reduced? Okay, this will be also affected on here. Okay, there it can show that blind spot detection at left side. Okay, now you can increment this, and now you can decrement this. It will give a right side. Okay, blind spot detection at right side. Okay, it is showing alarm as advertisery. Okay, you can see that graph, and here we are going to see that speedometer. We are reducing the speed. Why? Because we have given acceleration is very low, right? So it is reducing. So this is our project. Here we have connected. This is Python dashboard. Yeah, we did not see the regenerative braking, right? Just see this. I'm increasing my brake pedal. Here it will get starts charging. Okay, acceleration will be reduced. Here you can see acceleration is very less. My brake is 99%, so it will get charged from. It is very less amount of charge. Okay, will be produced, so that it will be implemented as a 0.1 or 0.05 change. Okay, so sometimes it may be shown, and sometimes it may be not changed also. Okay, this is our project. Thank you.